All right, so here we are with 9-4 geometric sequences and series. The previous lesson was arithmetic, and now we're moving on to geometric. Geometric sequences just means that you're going to multiply something now instead of adding or subtracting. And so we're going to find terms in the geometric sequence, find a geometric mean, and then also talk about sums in a series. So the first thing here is a geometric sequence, and it's the ratio of successive terms, and that is called a constant common ratio. So the idea is that there's this R value that's going to be multiplied by your previous term in order to get your next term. So instead of a arithmetic sequence, which had an addition that was going on, and we called that a common difference, we now have a common ratio. The common ratio cannot be 1 because if it's 1, then there is no change. Remember, multiplying by 1 gives the other number as the answer. So here's our recursive rule. Remember, the recursive rule says that if you want the next term or the nth term, you would take the previous term and then in this case now multiply by a common ratio, unlike in arithmetic, which was add. So the next piece here is just going to identify some geometric sequences and see if they work. We are also going to see if it happens to be arithmetic and then find that common ratio or difference if it exists. So taking a look at our first set here, I can definitely see that we are not growing exponentially because it turns out geometric sequences are exponential or fast growing or fast decreasing. And right here, it looks very much like we're going down by a little less than 10. So in that case, if I look at the difference between them, I am actually going down 7. So that means that our common difference is -7. And this happens to be an arithmetic sequence. All right, then the next one, let's see. We go from 180 to 90, so it's either subtracting 90 or half. Then we go from 90 to 60, and from 90 to 60, that's not half. It's actually a fourth from here to here. And 90 to 60, a half, a third, and a fourth. Oh, so that's not very helpful. So we're multiplying by a half or dividing by 2, multiplying by a 2/3. Is that what that is? 90 times 60. Let's see. Yeah, 2/3. That's weird. And then in this case, multiplying by a fourth. So definitely neither in this case because it is not a consistent subtraction each time, subtracting 90, subtracting 30, subtracting 45 somehow. And then this multiplier is not helping either. All right, so then we go to the next one where we go from 5 to 1 to 0.2 to 0.04. And so to get from 5 to 1, you could divide by 5, or you could subtract 4. But clearly to get from 1 to 0.2, you're not going to divide or subtract, sorry. But you could actually divide because 0.2 is actually 1/5. And then actually 1/25 is 0.04. And so you can see how this happens to be kind of multiples of dividing by 5. Now dividing by 5 is actually the same as multiplying by a fifth. And since we are talking about our definition of geometric being a common ratio that you're multiplying by here, so notice this image, that means that anytime that we see division, we're actually going to restate it as, anytime we see multiplication, we'll restate it as division. So in that case, I'm going to instead say that I multiply by a fifth to get from 5 to 1, and then multiply by a fifth to get from 1 to 0.2, and then from 0.2 to 0.04, we also multiply by a fifth, rather than dividing. So that means that our common ratio, R, is going to be 1/5, and then we're going to call it geometric because of that, because we are multiplying. All right. The next one here is our explicit rule, and just like the recursive rule, these can be found on your Chapter 9 test formula sheet. So up here is the recursive one that we saw earlier, where you need the first term, and then to get the next term, you multiply r by the previous term. And then right here is the formula we're going over right now. And that formula says that you're going to get any term number you want by taking the first term and multiplying by r, which is your common ratio, and then bringing that to the power of n minus 1. So n minus 1 is the power or the exponent. So just as you're looking at this, it's got a lot of symbols in it. So, all right. So the first thing we're going to do here is find the seventh term of this geometric sequence. So it does indicate that it's geometric, so we do know that there's a multiplier. In fact, as we look at the pattern, 3 times 4 is going to be 12. 12 times 4, again, is going to be 48. And then times 4 is apparently 192. All right. And they want you to find the seventh term. And remember that we are going to use the formula instead of just continuing this pattern 3 more times, because there will be moments in the test where you're asked to get the 127th term versus the 7th. And so you do want to be able to skip to that. So in order to do that, we're going to use the formula that we just got for explicit formulas, meaning we're going to be able to jump to whatever number we want, in this case 7. And so we're going to take a sub 1, which is our first term, and then multiply by r being raised to the n minus 1. So in this case, our n is 7, our a sub 1 is 3, and our r is 4. So you've got a lot of pieces over there, and a little bit clearer, I'll write them over here. So now we're going to plug them into our formula. We have a sub 7 is what we're looking for, and so we need to put a sub 1, which is 3, and multiply that by r, which is 4, and then raise that to the power of 7 minus 1. So when we look at this, this is technically up here in parentheses, and it's also an exponent. So according to the order of operations, we definitely want to be doing 7 minus 1 first. So we're going to go ahead and change that to 3 times 4 to the 6th. Then there are those of you that will think, oh, let's do 3 times 4 first, but remember that the order of operations, again, said to do our exponents in our parentheses, which we did, and now there's multiplication and division. We're still here on exponents. So 4 to the 6th is what we want to do next, and so this is going to be 3 times 4 to the 6th, and 4 to the 6th is 4,096. All right, and so then we're going to take that and multiply by 3. And so your answer is going to be 12,288, all for that 7th term. So a sub 7. And if that seems like a big number, that is why exponential growth is terrifying. Okay, so moving on to the next one here, just like we did with arithmetic, there will be ones where they give you kind of pieces of your terms here, and then kind of have some empty spaces between. So in that case, I'm going to find the 8th term of the geometric sequence. And so I'll do as I did in the arithmetic and make a table to talk about the pattern here. So up here we'll have our term value, and then this is going to be what happens when you plug it in. So we're starting at the 3rd value, and we do also have the 5th, but then we're trying to get to the 8th. All right, and so in order to do that, the 3rd term is 36, and then the 5th term is 324. So in that case, we are going to see what our common ratio is. And so you're going to ask yourself, what do I multiply? And that's r, to get to the 4th term. And then what do I multiply again to get to the 5th term? And so when we go through solving this, we're going to be saying that 324 comes from 36 times r times r, right? 36 times r gets that, times r gets that. But of course, we can rewrite that as 36 times r squared. And then we can go ahead and solve this. So in order to solve this, we're going to divide both sides by 36. And we get 9. And then that is going to equal r squared. And then in order to solve that, we're going to take the square root of both sides and get our result for the common ratio of 3. So now we know that our common ratio is 3, and so we can say that we would take 36 and multiply by 3 and get our fourth term, which is 108. Yep, there. And then we'd take 324 and multiply that by 3 and get 972. Multiply that by, 3, not 4, and get 2,916. And then multiply that by 3 and get 8,748. So your eighth term, or a sub 8, is 8,748. All right. So the next thing that we want to be just cautious about is when you're given two terms of a sequence, be sure to consider if they might be positive or negative values for r. So notice that we had a positive and a positive, and so technically I could have multiplied by a -3 and gotten negative 108, and then multiply by a -3 and get positive. So we could also have -3 equal r, because there is no indication that this term here is positive or negative. And so we could have that, which would mean that our result here would be positive, negative, positive, negative, positive, negative. So we could also have negative 8,748. It all just depends on if r is actually -3 or not. So we're just going to want to make sure that if we can, that we have an r that could be positive or negative. All right, so now we're on to geometric means, which hopefully you remember from geometry when we were talking about solving right triangles. But it turns out that if a and b are positive terms of a geometric sequence with exactly one term between them, the geometric mean given by the following expression actually gives you that number in between. So going back to this piece here, if you take the number 36 and multiply it by 34, again, there's one number between them, you could actually take the geometric mean of them, meaning multiply them, and then square root that answer, and you actually get back to 108. And so you can kind of fill in that missing piece, again, as long as it is only one term that is between them. So that's what's happening here. So geometric means are the terms between any two non-consecutive terms of a geometric sequence. So again, there is one term between them. And this will indicate the value of the number between. All right. So, for instance, let's say that we had a sequence that had 4/9 missing term and then 25/36. In order to get the geometric mean, to get the middle term, we would take 4/9 and multiply it by 25/36. Again, the whole idea is that this is your first term, this is your second term, and the geometric mean takes both of them and multiplies them, but then also square roots the answer. So once we multiply these, we're going to get 4/9 times 25/36 And so we get a fraction of 25/81, which I don't necessarily need a calculator to square root because this is actually the same as the square root of 25 over the square root of 81. And hopefully we know that the square root of 25 is 5 and the square root of 89 is 9. So the middle term between 4/9 and 25/36 would have been 5/9 if we were doing a sequence. All right. Then we have a series. And remember that series is adding each of the terms, okay? And so again, this formula will be given on our formula sheet here. So the partial sum, or S sub n, or later on we can do sigma notation, of the first n terms of a geometric sequence, so again, all of these added up, is going to be given by taking the first term and then multiplying that by a fraction of 1 minus r, the common ratio, to the n, or the term we're trying to get to, over 1 minus r. And again, r can't be 1. We've already talked about it, but also here because 1 minus 1 makes 0, and we can't divide by 0. So we are going to use that idea to find this sum. And again, very easily you could go ahead and just add all 8 numbers, but we are trying to use these formulas so we can get used to it and then also be able to apply it for a higher value. So taking a look at S sub 8, that means that n is 8. We also know that our first term is 1. And then the formula that we're trying to fill in says that we take that first number and multiply by the fraction of 1 over r to the n over 1 minus r. And so we do actually need the r value here in order to figure out what our sum is going to be. So in order to get from a 1 to a 2, we could either add 1, but of course we're doing geometric, so we're going to multiply by 2. And then we double check, 2 times 2 is 4, times 2 is 8, times 2 is 16. And so we do know that our r is multiplying by 2. All right, so then we're going to go ahead and fill in this formula. So we are taking S sub 8 because we're summing 8 terms. And then we'll have 1 times, which is really not that hard, 1 minus 2, because that was our r value, to the 8. And all of that is going to be over 1 minus 2. So as we've talked about before, fractions do actually potentially have a set of parentheses in the numerator and a set of parentheses in the denominator. And so when we think of order of operations, we are going to do these parentheses first, meaning the top and then separately the bottom. Once we evaluate the top doing PEMDAS itself and then the bottom doing PEMDAS, then we can start to divide. Okay, so the first thing that I'm going to do is the numerator. And so again, we have 1 times this fraction, so it's 1 minus 2 to the 8th. But 2 to the 8th is 256. And then that's still over 1 minus 2. Then we'll do a little subtraction to simplify this. So 1 minus 256 leaves us with negative 255. And then that's going to be over 1 minus 2, which is negative 1. So now that we've done the top separate from the bottom, we can now go ahead and actually divide them. So 255 divided by negative 1, both of these negative, means that we're actually going to have 1 times positive 255. And so, of course, 1 times anything leaves that 255 as the sum of the first 8 digits, or sequence values. All right. Our last example here jumps to sigma notation, but again, the same idea is happening here. So we can go ahead and sum the first 6 pieces. And remember that in order to sum the first 6 pieces, we are going to need our first term, and then we're going to multiply that by 1 minus r. So we are going to need to know our rate, and that's going to be brought to the number of terms we're adding, and then 1 minus r again. So again, I already know that n is 6 because that's the number above here. But then I need to find a sub 1. And a sub 1 comes when you take a 1 and plug it into this expression here. So a sub 1 is going to come from 1/2, and I'm going to plug in a 1 for this k. So that means that I'm going to have 1/2 raised to the 1 minus 1, which is 0. And so that means that my first term is 1. The first term is 1. The next piece is going to be our r. And so if we know what our a sub 1 is, we could take the time to do a sub 2, which means that we would plug in 1/2 and have 2 minus 1. And so that's going to be 1/2 to the 1. And so we're going to have a 1/2 for the second term. And so if you look at how you get from the first term to the second term, how do you get from a 1 to a 1/2? You're going to multiply by a 1/2. The other way that we could have realized that was going to say that this here being brought to a power is usually that rate that we're going for, that common ratio. So now we know that r is a 1/2. Either way. So now we can fill in that a sub 1 is 1. Our r is 1/2, so negative 1 minus a 1/2, and that 1/2 is being raised to the 6th, and then that's going to be over 1 minus another 1/2. Again, as we did before in the previous problem, we're going to do the numerator first, separate, then the denominator separate, and then we can divide them. I am no longer going to write this 1 times because that just seems ridiculous, so we're going to do instead 1 minus a 1/2 to the 6th. And that is 1/64. On the bottom, we still have 1 minus a 1/2, and now we can go ahead and subtract them. So 1 minus 1/64 leaves us with 63/64, and that's going to be divided by 1/2. You can use your calculator to divide this, but remember that when you're dividing fractions, you're just multiplying by the reciprocal. So 63/64 times 2 over 1, the flip of this, leaves us with 63 divided by 32, which I don't think does much. Nope. So 63 62nd. Oh, sorry, 30 seconds. That's a 3. Which we could also say is 1.96875. All right. So kind of a lot of work to go through that because, again, we had to find our r. But if you do recognize this as the rate, especially when we think of a exponential function, this thing being brought to the power is your rate or of change. So in that case, you could have kind of skipped this step here. All right. So that is your 9-4 notes of your geometric sequences. So hopefully we remember a geometric mean. Remember that's the multiplication of 2 values to find the middle term and then the square root of that. We also have a geometric sequence, which comes from multiplying, and then the series comes from that multiplication, but adding each of the terms.